Welcome back to the Deep Dive, the resource that strips away the noise and delivers only the essential insights you need to know. Today we are embarking on, well, the ultimate technical journey. We're not just building a system, we're scaling it, starting from the simplest single box and charting the course, decision by decision, all the way to handling tens of millions of users around the globe.
That's quite a journey, a marathon, definitely not a sprint. Our mission today really is to follow that progression. You can be painful, sure, lots of technical debt, architectural refinement, but we're going to extract that handful of, vital techniques, the ones that underpin every major internet application. We'll focus heavily on the trade-offs, the complexity that creeps in with every new layer of infrastructure.
Okay, let's unpack this. Every big success story starts small, right? So
Yeah.
our starting line is the simplest concept in system design. The monolithic single server setup. You've got the web apps, the database, maybe some basic cache, all running on one machine. It's cheap, easy to manage at first, but yeah, inherently brittle.
Brittle is exactly the right word. I mean, when traffic is basically zero, it works fine. But to really get why we need to scale, we have to understand the fundamental flow of a request first. So you, the user, you access a website via its domain name, let's say api.mysite.com.
Right, and that domain name lookup, that's step one, handled by the DNS, the domain name system. DNS itself is this huge, distributed global thing, but its job is pretty straightforward. Turn that human-friendly name into the IP address the computer needs, something like 15.125.23.214.
Exactly. Your browser, or maybe your mobile app, gets that IP address back. Then it sends an HTTP request straight to our lonely little web server. The server does its thing, runs the business logic, queries the database right there on the same box, calculates whatever it needs to, and then finally it sends back the response. Could be an HTML page, could be JSON data.
And this traffic, it's coming from different places these days. Our sources point to two main consumers hitting that server. You've got the classic web application. It uses server-side languages, maybe Python or Ruby for the heavy lifting, the logic. But what the user actually sees and interacts with is client-side stuff, HTML, CSS, JavaScript.
Yeah, and then you have the mobile apps. They usually skip all the HTML rendering. They talk almost entirely via APIs over HTTP. And they're usually grabbing data in JSON format because it's lean, efficient. So if you open a friend's profile on your phone, the app is probably making a very specific API call, maybe get GD users 12, and it expects that JSON object back.
Okay, so we have a clear basic flow, but the minute user traffic picks up even just a little bit, that single server gets hammered. The database might eat all the RAM, starving the web app, or maybe the other way around. You hit the physical limits of that one box really fast. And that failure, well, that pushes us directly into the first big architectural change.
Right. The absolute first logical step, the moment your CPU or memory usage starts spiking regularly, is separation. You've got to move the database off the web server, give it its own dedicated machine.
Okay, and that's more than just shuffling files around. This creates two distinct layers, or tiers. You've got the web mobile traffic tier, handling user connections, running the code, managing sessions, and then the data tier, which is purely focused on storing and retrieving data, persistence.
And the crucial benefit here, the reason you do it, is flexibility. Suddenly, you can scale these two pieces independently. If your app needs a ton of processing power, lots of calculations, you add more web servers. If it's mostly about handling data, lots of complex queries, you beef up the database server.
Makes sense. But separating them forces this really foundational decision, one that echoes through all future scaling, the database dilemma. SQL or no SQL?
Yeah, this is a big one. Historically, relational databases, RDBMS, SQL databases like MySQL, PostgreSQL, SQL Server, they were the default, still are, often. They structure data very rigidly, tables, rows. They stick to the ACD properties, atomicity, consistency, isolation, durability. Their real power comes from efficiently handling complex join operations across different tables.
Right, the classic choice. And often the safest, especially if you're dealing with things like financial transactions or critical inventory, those transactional guarantees from SQL are super valuable.
Absolutely. But, the landscape's changed. Non-relational databases, NoSQL, are major players now.
Yeah.
They come in different flavors, key value stores, graph databases, column stores, document databases. Popular examples, things like Cassandra, Neo4j, Amazon DynamoDB. The core trade-off is usually this. You often gain flexibility and potentially speed, but you generally lose the ability to do those complex joins easily or quickly.
And that rigid structure of SQL, that can be a scaling issue in itself, can't it? Like, if your application is changing fast, the schema needs constant updates, adding columns, changing tables. SQL can mean downtime or really complicated migration processes.
Oh yeah, that's a huge operational headache. In contrast, a lot of NoSQL databases are schemaless or schema-light, so your development team can move faster. They don't have to sync up every tiny data model tweak with DBAs or write complex migration scripts.
Okay, so SQL is often the safe default. But when do the sources suggest really considering NoSQL? Looks like there are about 4 key scenarios where it might be the right move.
Yeah, 4 main drivers. First, when you need super low latency, like we're talking milliseconds. A distributed NoSQL system can sometimes bypass the internal complexity and overhead of a traditional SQL engine, giving you faster reads and writes.
Okay, speed. What else?
Second, the data itself. If your data is just messy, highly unstructured, or maybe it doesn't really have relationships between different pieces of data, think log data, sensor readings. Trying to force that into neat rows and columns can be really inefficient. So if linking tables doesn't add value, NoSQL might fit better.
Right, if the data doesn't naturally fit that table structure. Third.
Third, if your main job is basically just serializing and deserializing data, meaning you're constantly saving and loading big chunks of data, maybe formatted as JSON, XML, or YAML, NoSQL databases, especially document stores, often handle that kind of task more naturally and faster than translating those structures into SQL rows and back again.
Makes sense. And the last one.
Finally, just sheer scale, raw size. If you're looking at storing a truly massive amount of data like petabytes, well, non-relational options that were built for huge horizontal distribution like Cassandra start looking a lot more attractive than trying to scale up one giant SQL server or dealing with really complex SQL sharding early on. But the key thing to remember is the trade-off. Choosing a distributed NoSQL store might seem modern, but it often pushes complexity onto your application developers. Suddenly, they have to worry about data integrity, lack of transactions, eventual consistency. Things SQL used to handle for them.
Okay, so we've separated our tiers, web server here, database server there, but inevitably both start hitting their limits again. Separation just bought us some time. So that leads us to the real strategy for growth: horizontal scaling and redundancy.
Right, this is where we formalize the choice. You've got 2 main paths to grow. There's vertical scaling, or scaling up.
Yeah.
That just means throwing more power at your existing servers, faster CPUs, more RAM.
Which sounds simple, easier to manage one big machine, maybe?
It is simpler initially, but the limitations are, well, they're pretty serious. First, there's a hard physical limit. Servers only get so powerful, eventually you max out. And maybe more importantly, it's a single point of failure, SPOF. If that one massive server goes down, your whole application is offline, period.
It's not good. So the alternative is horizontal scaling or scaling out. This is the preferred way for big applications, right?
Definitely. Scaling out means adding more servers to your pool. Often they're less expensive, commodity machines.
Okay, so this gets around the hardware limit, and it builds in redundancy from the start.
Exactly. It addresses both major limitations of scaling up.
But wait, if we now have, say, 5 web servers, how do we manage all the incoming user requests? How do we make sure they're spread out evenly? We need some kind of traffic controller.
Precisely. You need a load balancer, or LB. The load balancer sits right at the front door of your infrastructure. Its main job is to distribute incoming traffic evenly across your pool of web servers. This could be simple round-robin, like dealing cards, or smarter, based on which server is healthiest or has the least load right now.
And here's a key security point from the sources. Users connect to the load balancer's public IP address, the one DNS gave them. But the web servers themselves, they sit behind it using private IP addresses. They're essentially hidden from the public internet.
That's a critical design pattern. It means external clients can't hit your application servers directly. Adds a really important security layer, helps mitigate attacks.
And this LB setup is what gives you high availability, right? What happens if one server just fails?
Yep. If web server 1 suddenly goes offline, maybe it crashed, maybe it's down for maintenance, the load balancer detects it's unhealthy, instantly it stops sending traffic there and routes everything to the remaining healthy servers in the pool. And later, when traffic grows, you just add new servers to the pool behind the LB, and it starts bouncing traffic to them automatically.
Yeah.
Seamless.
Okay, web tier redundancy solved. But we need the same kind of resilience for the database. So we need database replication, usually using the master-slave model.
Correct. In this model, you designate one database server as the master. It handles all the write operations, inserts, deletes, updates. It's the primary source of truth. Then you have one or more slave databases. They get copies of the data from the master through a replication process. And critically, they only handle read operations.
Okay, so one writes, the others read. That makes sense because most apps do way more reading than writing, right? Like scrolling feeds versus posting one update.
Exactly that. The read-to-write ratio is often heavily skewed towards reads. That's why you typically see systems with many slave databases, but only one, or maybe a few, masters. And the advantages are pretty clear. First, better performance. You can spread all those read queries across multiple slaves, processing them in parallel, big throughput boost.
Okay. Performance. What else?
Second, reliability. If something catastrophic happens, like a server is literally destroyed in a fire or flood, your data isn't lost. It exists on the replicated slave nodes, ideally in different physical locations.
Like disaster recovery. And the third?
High availability. If one database server goes offline temporarily, maybe for patching or minor issue, the system keeps running. Reads can go to other slaves, writes still go to the master, assuming it's up.
This sounds pretty robust. But what happens when things actually fail? Especially if the master fails. That sounds tricky. If a slave fails, okay, reads go elsewhere. Manageable?
Right. If a slave fails, you redirect reads temporarily, maybe to the master if you only have one slave, or to other healthy slaves if you have several. Then you fix or replace the failed slave. But yeah, if the master fails, that's a different level of problem. Yeah, it's often an operational all-hands-on-deck situation. You have to promote one of the healthy slaves to become the new master. This usually involves running automated scripts, sometimes manual steps, to make sure the transition is clean. Then you need to spin up a new slave to replace the old promoted one and get replication flowing again.
And here's where it gets complicated, right? When you promote that slave, how do you know it was perfectly, absolutely up to date with the old master right before it died?
You've hit the nail on the head. Not always, especially if you're using asynchronous replication, which is very common because it's faster. Asynchronous means the master sends the update, the slave acknowledges it quickly, maybe before it's fully written the data to its own disk. This creates a small window, potentially milliseconds, where if the master fails right then, the slave might not have the very last transaction, a small risk of data loss.
Okay, so there's this concept, RPO, recovery point objective. If you need an RPO of 0, absolutely no data loss ever, you'd need synchronous replication.
Correct. Synchronous replication means the master's transaction is only considered fully complete after the slave confirms it has successfully written the data, guarantees consistency, but the downside is huge latency. Every single write operation now has to wait for that round-trip confirmation from the slave. It can really slow down the user experience.
Wow, okay. So it's a brutal trade-off. Do you choose perfect consistency but potentially slower performance using synchronous replication? Or do you choose much better speed and accept a tiny risk of losing the absolute latest data in a rare master failure scenario using asynchronous replication?
In most large-scale consumer apps, they choose asynchronous. They accept that very low risk. They might need data recovery scripts to reconcile tiny inconsistencies after master promotion, but they prioritize keeping the overall system fast and responsive for users.
Okay, we've got redundancy now, a resilient web tier, a replicated, resilient data tier. Our system can handle failures. But stable doesn't always mean fast. We need speed. Which brings us to phase 3, optimizing performance with cache and CDN.
Cache is our #1 tool for speeding things up internally. Think of it as temporary super-fast storage for data that's expensive to compute or retrieve from the database or just access really often. It's typically stored right in memory, RAM. The principle is simple. If hitting the database takes, say, 50 milliseconds, grabbing it from an in-memory cache might take less than 1 millisecond. Huge difference.
And just like we separated the database, we should separate the cache too, right? Put it in its own cache tier.
Absolutely. You never want your cache fighting your web application for precious memory or CPU cycles on the same machine. Separating it dramatically reduces the load on your database, fewer queries hit it. And it lets you scale the cache layer independently. Need more cache? Add more cache servers. The typical way it works is using a read-through cache strategy. The web server checks the cache first when it needs data.
Okay, so request comes in, web server looks in the cache. If the data's there, that's a cache hit, boom, serve it instantly, fast. If it's not there, a cache miss, then the web server has to go ask the database.
Right. It queries the database, gets the response back. But before sending it to the client, it stores a copy of that response in the cache.
Right.
Then it sends the response to the client. The next user asking for the same data gets a cache hit.
Sounds great, but I bet there are complications, cache considerations, as the sources call them. What are the big ones?
Oh yeah, the devil's in the details.
Yeah.
First, the use case. Cache is perfect for data that's read a lot but doesn't change very often. Think user profiles, product catalogs maybe. It is not for permanent storage. Remember, it's usually in memory. If a cache server restarts, poof, that data is gone. You need the database as the source of truth.
Gotcha. What about keeping the data fresh? You can't just cache stuff forever.
Exactly. That's the expiration policy, or time to live, TTL. You have to set a timer on cache data. Set it too long, users might see old, stale information. Set it too short, and you're constantly going back to the database anyway, kind of defeating the purpose of the cache. Tuning TTL is a constant balancing act.
So TTL is critical. What else? Consistency sounds like a nightmare.
It is the major challenge. How do you keep the data in your fast temporary cache in sync with the permanent data in your database? When data gets updated in the database, you need a way to either remove, invalidate the old copy from the cache, or update it with the new value. This is hard enough with one cache server. But when you have multiple cache servers, maybe spread across different regions, it gets incredibly complex.
Yeah, the sources mentioned Facebook's struggle scaling Memcache globally. It wasn't just about speed, but handling these cache invalidation storms.
Right. If a really popular item changes and its cache entry expires everywhere at once, you can get thousands of requests suddenly bypassing the cache and slamming the main database simultaneously. The thundering herd problem causes massive load spikes.
Yikes. Okay, so what about the cache servers themselves failing? They're fast, but they can still go down.
Good point. A single cache server is just another SBOF. So you always deploy multiple cache servers. Often you use techniques like consistent hashing to spread the cache data across the pool of servers. And you typically over-provision memory, maybe have 20–30% more RAM than you think you need right now. That gives you a buffer if one server fails or if you have unexpected traffic spikes.
Okay, multiple servers, extra memory. But what happens when the cache does get full? You have to kick something out to make room for new stuff. Eviction policies.
Yep. You need a strategy for deciding what gets booted when memory is full. The most common one by far is LRU, least recently used.
Why LRU? What's the logic?
LRU works on the idea of temporal locality. Basically, data you just accessed is likely to be needed again soon. So it makes sense to evict the item that hasn't been touched for the longest time. But it's not the only way. Depending on your specific needs, you might use LFU, least frequently used, keeping the most popular items regardless of when they were last accessed, or maybe even FIFO, first in, first out. If you just want to clear out the oldest stuff quickly, LRU is usually the default starting point, though.
Okay, cache handles internal data speed. Now let's look outward. Static files, images, CSS, JavaScript, videos. That's where the Content Delivery Network, or CDN, comes in.
Exactly. CDN is all about geography. It's a network of servers spread all over the world, often called points of presence or POPs. The whole idea is to get static content physically closer to your users. The fewer network hops the data has to travel, the faster it arrives. So if your main servers are in, say, Virginia, but a user is in London, a CDN POP in London can serve them images much, much faster than pulling them all the way across the Atlantic.
Right. So walk me through the flow. User needs an image, like logo.jpg. The URL points to the CDN, maybe https://mycdn.com logo.jpg.
Yep, something like that. The user's request automatically gets routed, usually by DNS magic, to the nearest CDN POPy.
If that POPy has the logo.jpg cached,
It serves it instantly, super fast. That's a CDN cache hit. If it doesn't have it a cache miss, the CDN server goes and asks the origin for the file. The origin is usually your main web server or maybe dedicated cloud storage like Amazon S3. The origin sends the file back to the CDN POPy. It might also include a TTL header telling the CDN how long it's safe to cache this file.
Gotcha. And from then on, until that TTL expires, the CDN serves that logo directly to anyone else nearby who asks for it. It takes a huge load off our main servers.
Precisely. Offloads bandwidth, reduces latency. It's fundamental for good web performance.
Okay, but CDNs aren't magic. There are specifics to consider. Cost, for one.
Big one. CDNs are typically third-party services, and they charge you based on how much data gets transferred out of their network. Egress. So you need to be smart about what you cache. Cache the stuff that gets hit, often logos, CSS, main.js files. Caching massive video files that only get viewed occasionally can get expensive fast.
Right. And what if the CDN itself has problems? They can go down too, right?
They got that, though, usually briefly or regionally. You absolutely need a fallback mechanism in your application. Your website or app should be able to detect if a CDN resource isn't loading and automatically try to fetch it directly from your origin server instead. The user experience shouldn't completely break just because the CDN hiccuped.
Good point. Need a plan B. And finally, what about updates? If I change my company logo, I don't want the old ones stuck in the CDN for days until the TTL runs out. How do you invalidate files?
Yeah, that's crucial. You can usually use the CDN provider's API to manually purge specific files from their cache. But the most common and often easier way is object versioning. You just change the file name slightly, usually by adding a version parameter to the URL. So instead of logo.png, you use logo.png.va2. Or maybe logo-v2.png. This makes the CDN see it as a brand new file it hasn't cached before, forcing it to fetch the updated version from your origin.
Okay, incredible progress. We have a robust, fast system, redundancy, replication, cache, CDN. We're handling load much better. But as we aim for massive scale, millions of users online at the same time, there's one huge bottleneck introduced by horizontal scaling that we absolutely have to fix: server state. So phase 4 starts by making the web tier completely stateless.
This is non-negotiable for large-scale systems. It's a fundamental architectural shift. The problem with this stateful architecture is that the web server itself holds on to client-specific data in its own memory. Things like session info, what's in your shopping cart, who you are right now. So if user A logs in and their session starts on web server 1, the load balancer has to make sure every single subsequent request from user A goes back to that specific server, server 1.
Right, that's often done with sticky sessions on the load balancer, which sounds helpful, but it actually messes things up, doesn't it?
Totally messes things up. It prevents true, even load balancing across all servers. It makes adding or removing servers really complicated because you have to drain connections gracefully. And critically, if server 1 crashes, user A's session data, their shopping cart, everything's stored in that server's memory. It's just gone. They get logs out, lose their work. Bad user experience.
Okay, so how do we fix it? What's the stateless solution?
You move all that temporary user-specific state out of the web server's memory entirely. You put it into a shared external data store that is persistent and highly available. This is often a fast, scalable, NoSQL key value store like Redis or Memcached, maybe configured for persistence.
Ah, okay. So the web servers themselves become dumb processing units. They don't hold on to any user data between requests.
Exactly. Now, any incoming HTTP request from any user can be sent to any available web server by the load balancer. The web server gets the request, maybe quickly fetches the user session state from that external store, like Redis, does its processing using that state, maybe updates the state in Redis, sends the response back, and then essentially forgets about that user.
Wow, okay, that's huge, because now adding or removing web servers becomes trivial.
Completely trivial. It enables true, seamless, automated scaling, auto-scaling. You can set up rules. If average CPU across the web tier goes above 70%, automatically add 2 more servers. If it drops below 30%, remove one. You don't have to worry about migrating sessions or breaking sticky configurations. It just works.
Brilliant. Okay, with auto-scaling and a stateless web tier, we can now realistically think about supporting multiple data centers, taking the application truly global.
Right. The motivations here are usually twofold. First, even higher availability. If an entire geographic region has an outage, power grid failure, major network issue, your application can stay online, serve from another region. And second, user experience. Putting data centers closer to your major user bases drastically reduces latency. Users in Europe get faster responses from a European DC than one in the US. So maybe US East and US West, or US Europe and Asia.
So how do you actually direct users to the right data center? Is it just based on where their IP address seems to be?
That's the starting point. GeoDNS, or georouting, is the technology here. At its simplest, it looks at the source IP of the DNS query and directs the user to the data center that's geographically closest. But more sophisticated GeoDNS services often do more. They might incorporate real-time latency measurements. They actively probe network paths to figure out which data center is actually fastest for that user right now, not just closest. Sometimes odd network peering means a slightly farther fun. DC is actually quicker.
Clever. Okay, and what about a major disaster? Say the whole US East data center goes offline.
That's the failover scenario. The monitoring systems detect the widespread outage in US East. The GeoDNS configuration gets updated, often automatically, and boom, 100% of the traffic that was going to US East is now rerouted to the next closest healthy data center, maybe US West or Europe.
Sounds essential for global scale, but running multiple DCs must come with its own set of challenges. Data synchronization seems like the biggest one.
It absolutely is. You have users potentially writing data to local databases in different regions simultaneously. How do you keep all that data consistent across the globe?
You mentioned asynchronous replication earlier for master-slave within a DC. Is it the same idea between DCs?
Pretty much, yeah.
Yeah.
You almost always have to rely on asynchronous replication between data centers. Trying to do synchronous replication across oceans would introduce massive delays for users. Waiting for confirmations from halfway around the world, it would kill performance.
Okay, so you prioritize availability and speed over perfect, instantaneous consistency between regions. Like Netflix, apparently.
Exactly. Netflix is a great example. If you update your viewing history or rating in the US, that update might take a few seconds, maybe longer, to replicate and show up if you immediately flew to Europe and logged in there. They accept this eventual consistency because the alternative, making US users wait for European servers to confirm every action, would make the service feel sluggish. You trade immediate global consistency for local speed and availability.
Back to that core trade-off again. Speed versus consistency. You design to fail gracefully if sync is briefly delayed, rather than failing slowly all the time due to network latency.
Yep. And beyond sync, just managing multiple DCs requires rock-solid testing and deployment practices. You need serious automation, continuous integration, and continuous deployment CI/CD pipelines to ensure that when you roll out a new version of your code, it gets deployed identically and functions correctly in all your data centers simultaneously. Inconsistent deployments are a common cause of regional outages.
All right, we've gone global. We have stateless auto-scaling web tiers, multiple data centers, but systems can still get bogged down by slow internal processes. How do we build resilience against those? This brings us to phase 5, decoupling system components using message queues.
Message queues, or MQs, are essentially durable buffers, usually stored in memory but often backed by disk for persistence. Their core job is to enable asynchronous communication between different parts of your system. The goal is decoupling breaking dependencies so that scaling or failure in one part doesn't immediately take down everything else.
Okay, so how do they work? Is it like sending emails between system components?
Sort of, but more structured and reliable. You have producers or publishers. These are parts of your system that create messages. A message usually represents a task that needs to be done. They push these messages onto the queue. Then you have consumers or subscribers. These are separate processes or services that connect to the queue, pull off messages one by one, and perform the action defined in the message. Crucially, they do this work asynchronously on their own schedule.
Gotcha. So give me an example, maybe not photo processing, but something like e-commerce checkout.
Perfect example. When a customer completes an order, the main web server needs to process the payment and maybe decrement inventory right away. That has to be synchronous, immediate.
Right, can't delay taking their money.
Exactly. But what about sending the confirmation email? Or notifying the shipping warehouse? Or calculating loyalty points? Or updating the sales analytics dashboard? Those things are important, but they don't need to happen instantly while the user is waiting.
Ah, I see. So the web server handles the critical payment inventory part.
And then it just publishes messages to different queues. Send order confirmation email 123, notify warehouse order 123, update analytics order 123. It does this super fast and then immediately tells the user, success, your order is complete. Meanwhile, separate worker processes, the consumers are listening to those queues. An email worker picks up the email task, a warehouse worker picks up a notification task, and so on. They do the work in the background, the user gets a fast response, and the core system isn't blocked waiting for, say, a slow email service.
That's clever. And the scaling benefit seems huge, too.
Massive. The producers,
Yep.
web servers, and the consumers, worker processes, scale completely independently. If you have a huge sale and suddenly the notify warehouse queue starts backing up with thousands of messages, you don't need to touch the web servers. You just spin up, say, 50 more warehouse worker processes temporarily to chew through that backlog. When the queue drains, you scale the workers back down. Total flexibility.
Okay, decoupling is powerful. Before we hit the absolute final boss of scaling the database itself, we need to talk about operational stuff. Things you just have to do once your system gets this big and complex: logging, metrics, automation.
Non-negotiable. You're flying blind without them. Logging is essential for debugging, for understanding what went wrong after an incident, and for spotting errors in real time. And we're not talking about just tailing log files on individual servers anymore. You need centralized logging aggregation tools. Think Elasticsearch, Splunk, Datadog logs. You need structured logs, maybe JSON formats, so you can easily search, filter, and analyze logs across thousands of servers.
Right, gotta find the needle in the haystack.
And metrics. Metrics are the pulse of your system. You need to track several levels. Host-level metrics, CPU usage, memory, network I/O, disk space on individual machines. Aggregated level metrics, the overall performance of entire tiers. How many requests per second is the database tier handling? What's the average latency for the cache tier? And crucially, key business metrics. How many daily active users, DAU, do we have? What's our user retention rate? How are users moving through the conversion funnel? How much revenue are we making? These business metrics often drive the technical scaling decisions. Tools like Prometheus for collecting and Grafana for visualizing are industry standards here.
Makes sense. Track everything. And automation.
You can't manage this scale manually. You need automation everywhere. Continuous integration CI systems are vital. Every time a developer checks in code, automated tests run to catch bugs early before they hit production. And continuous deployment, CDE pipelines automate the process of building, testing, and rolling out new code versions safely and consistently across all your data centers. It keeps developer velocity high and reduces human error during deployments.
Okay. Logging, metrics, automation table stakes for large scale. Now, the final frontier. The database. We use replication for read scaling. But what happens when the master database itself runs out of space? Even those monster servers with 24 terabytes of RAM hit limits or just can't handle the sheer volume of writes anymore. We have to scale the database horizontally. We need database sharding.
This is often considered the hardest part of scaling. Let's quickly revisit why vertical scaling isn't the answer here. Hardware limits, crazy expensive costs for those monster servers, and you still have a single point of failure for writes if you only have one master. Sharding is the way you scale out the data tier itself.
Okay, so what is sharding fundamentally?
It means splitting one logically huge database into many smaller, physically separate databases, called shards. Each shard contains only a subset of the total data. They usually all share the same schema, table structure, but hold different rows. So instead of one 50-terabyte database, maybe you have 50 shards, each holding 1 terabyte. Much more manageable.
And how do you decide which piece of data goes into which shard? That sounds critical.
It is the critical decision. Choosing the sharding key, sometimes called the partition key. This is the piece of data used in a function to determine which shard a particular row lives on. Often it's something like a userid or maybe a customrid or tenanted. A simple approach might be a hash or modulo function, like userid%n, where n is the number of shards. User 1 goes to shard 1, user 2 to shard 2, t, user n plus 1 back to shard 1.
Okay, but the choice of that key has huge implications, right? If you shard by userid, finding all data for one user is easy. It's all on one shard. But what if you need to find all users in a specific city?
Exactly. If your key is userid, a query based on city might have to hit every single shard to find all the matching users. This is called a scatter-gather query, and it kills performance. It kind of defeats the purpose of sharding. If you choose tenanted in a multi-tenant app, all data for one customer is nicely co-located, simplifying queries for them. But what if one tenant is absolutely massive compared to others? You could end up with one shard being overloaded while others are nearly empty. Big imbalance.
Right. Choosing that key carefully based on your main query patterns is vital. And this complexity leads directly into the major challenges of sharding. Challenge 1, resharding.
Ugh, yes, resharding. This happens when you need to add more shards because existing ones are full, shard exhaustion. Or maybe your initial sharding key choice led to uneven data distribution. You have to change your sharding logic. For example, go from userid per 4 to userid per 8, and then physically move potentially terabytes or petabytes of data between servers, all while keeping the application online. It's incredibly complex, very risky, and often requires careful planning and potentially downtime or maintenance windows.
Sounds painful. Okay, challenge 2, the celebrity problem, or hotspot key.
Yeah, this is related to the uneven distribution issue. If you shard by userid, what happens when a user with massive activity, think Katy Perry, or maybe a huge corporate account generating tons of data lands on a particular shard? That one shard might suddenly get hammered with 90% of the traffic, while all the other shards are relatively idle. The load isn't balanced at all. That specific user becomes a hotspot.
That completely breaks the scaling model. How do you even mitigate that? You can't tell celebrities to be less popular.
No. Architecturally, dealing with hotspots often involves moving beyond simple modulo hashing. Techniques like consistent hashing help minimize data movement during resharding and can distribute load slightly better. But for extreme hotspots, like that celebrity example, the common solution is often to identify those keys and give them their own dedicated shard, or even further subdivide their data onto multiple dedicated shards. It's basically manual intervention to isolate the problem.
Wow, okay. Dedicated shards for specific users. And the final big challenge, joins and denormalization. SQL loves joins, but
Joins become incredibly difficult and slow across shards. If you need data from table A on shard 1 and table B on shard 2 to satisfy a single query, you typically have to create both shards independently and then have your application layer stitch the results together. It's slow and complex.
so it's the workaround.
Denormalization. You often have to intentionally duplicate data. So if you frequently need user profile information when querying order data, even though profiles live on a different shard, sharded by userid, You might copy some key profile fields, like username or email, directly into the order records, sharded by ordered or customized. This makes the data less normalized in the traditional database sense, but it allows many common queries to be satisfied by hitting only a single shard, avoiding those costly cross-shard joins. You trade storage space and some consistency complexity for query performance.
What an incredible, complex journey. We literally went from one single server, and through dealing with failure after failure, bottleneck after bottleneck, we've architected this incredibly sophisticated system. Load balancers, replicated databases, multiple cache layers, CDNs, message queues for decoupling, stateless web tiers, multiple data centers, and finally sharded databases with all their complexity, maybe even some specialized NoSQL stores mixed in.
Exactly. If you look at a diagram of a system like this, like Figure 123, often shown in these discussions, it incorporates all those pieces working together. It's the culmination of addressing all those scaling pain points.
So if we had to boil this whole deep dive down, what are the core strategies? The absolute must-dos for scaling to millions. Looks like maybe 8 key things emerged.
Yeah, I think we can summarize it that way. 8 essential pillars.
Okay, number 1. Keep that web tier completely stateless, absolutely critical for easy scaling and resilience.
2, build redundancy at every tier.
Yeah.
Load balancers, multiple web servers, replicated databases, clustered caches. Eliminate single points of failure wherever possible.
3, cache data aggressively. Use caches for anything you can to reduce database load and improve speed, but manage those TTLs and consistency carefully.
4, support multiple data centers for global reach and high availability. Use smart routing like GeoDNS.
5, host static assets images, CSS/JS on a content delivery network, CDN. Get content closer to users, save your bandwidth.
6, scale the data tier itself when needed, usually through horizontal sharding. Accept the complexity, choose your sharding key wisely, plan for resharding and hotspots.
7, split your system into individual services where it makes sense. Decouple components using things like message queues so they can scale and fail independently.
And finally, 8, monitor everything meticulously. Use structured logging, collect detailed metrics, system and business, and automate everything you possibly can, especially testing and deployment, CI/CD.
That roadmap seems to cover the journey to supporting millions of users, a globally distributed, stable performance system. But here's the final thought for you, our listeners, to chew on. We got this far through continuous iteration, solving one problem after another. What's the next inevitable step beyond millions? It's probably not just tweaking these existing components. It often involves even more aggressive decomposition, breaking down these tiers and services into even smaller, more specialized, independently deployable units. The move towards fine-grained microservices.
Because in system design, the quest for the perfect, smallest, most independent, most resilient unit of work, well, never really ends, does it?
The learning definitely never stops. Thanks for joining us for this deep dive. We'll catch you next time.